Hello and good evening, everyone. Welcome back to the second TA session of Drug Delivery Principles and Engineering. We'll wait for a few more minutes to let everyone join and then we'll start.
Good evening, sir. I'm unable to hear your voice, sir. Hello. Good evening, sir.
Hello, can you
Yeah.
hear me now? Hello.
Yeah, ma'am. Ma'am, now okay, ma'am. I'm able to hear your voice.
Okay.
Okay, thank you, ma'am.
We were waiting for some more time to let others join, and
Yeah, yeah.
after that we'll start. Yes.
Yeah, okay, ma'am.
We'll wait for one more minute and then we'll start.
Yeah.
Okay. So, hello everyone. For those who joined today, I'm Bhagyashri Pradhan, one of the TAs of Drug Delivery Principles and Engineering. And before we proceed, I want to let you guys know that this session is being recorded and will be shared on YouTube. And did you guys receive the link for the last session's link? That was also recorded, and it was, I think the link was shared with you. Did you guys receive the link? Can anyone unmute and let me know?
Yes, ma'am.
Okay, okay, thank you. Okay, I think you guys had your first assignment due last week. Did you guys all submit the assignment? Hello.
Yes, ma'am.
Okay. If you guys had any problems in solving those questions, we can discuss those as well. And today we'll discuss previous year assignments that will be helpful in solving your new assignment that is upcoming in this week, and it might also help you in the exam. Okay, so we will start. Can you guys see my screen now?
Yes, ma'am.
Okay. Did you guys go through the last week's lectures? Hello. Can someone unmute and let me know if you guys went through last week's lectures? Okay. Can I assume that you guys didn't go through the lectures?
Yes, ma'am.
Okay. No issues. We'll still try to solve the questions. Okay. So to give a context, the topics that were covered this week were biomedical polymers, polymer drug conjugates, diffusion control system, controlled release reservoir system. I won't be going in details in this on these topics. You guys can refer to the NPTEL lectures, but we'll discuss some of these while going through the questions. Okay. So the first question is, for a given polymer, rank Tg, that is glass transition temperature, Tm, melting point, and Tc, crystallization point from lowest to highest. You guys can unmute yourself and let me know the answers. Here is the question again. For a given polymer, rank Tg, that is glass transition temperature, Tm, melting point, and Tc, crystallization point from lowest to highest. Anyone would like to volunteer to answer this question?
I think second option.
Just a second. Second option, Tg, Tc, and then Tm. Anyone else?
Ma'am, option number 4.
4. Tm, Tc, and then Tg. Okay. Anyone else?
EG, TC, TM, ma'am.
The last option.
Tc, Tg, Tm. Yes. Anyone else wants to answer?
The second last option.
Tc, Tm, Tg. Okay. Okay. We'll now see the answer. The answer is Tg, Tc, and Tm. That is the second option. I think the first person that answered this was correct. Okay, so Tg is the glass transition temperature, the temperature at which the polymer undergoes a transition from a hard glassy state to a rubbery state. And then it comes Tc, which is the crystalline temperature, and it will form crystalline. And after forming the crystalline, then comes the Tm, that is the melt transition temperature, the temperature at which all crystalline regions melt. that is crystallinity disappears. That's why first Tg will come, then Tc, and then Tm. Is that clear?
Yes, ma'am.
This plot was explained in the NPTEL lectures. If you guys go through the lectures, you'll be able to understand this in more detail. So first the glass transition temperature, and then the glass crystalline temperature, and then the melting temperature will come. Melting temperature is the highest temperature. Okay, we'll move on to the next question. Which of the following statements is not a limitation of polymer drug conjugates? Choose two statements. Which of the following statements is not a limitation of polymer drug conjugates? So you need to find the advantages of polymer drug conjugates. Anyone would like to volunteer? Which of the following is not a limitation of polymer drug conjugates?
The last option.
Last option and polymer drug conjugate can improve bioavailability of many poorly soluble drugs.
Okay. And the last option you said, right?
Yes, ma'am.
Okay, good. Anyone else?
Bioavailability can be improved
Okay.
and it can be made targeted for specific application.
Okay. Yes, anyone else? Anyone else would like to answer?
Yeah, fifth and seventh.
Okay. Okay. You guys are all correct. So the options will be polymer drug conjugates can improve bioavailability of many poorly soluble drugs, and polymer drug conjugates can be made targeted for specific applications. This is how basically a polymer drug conjugate would be, where we can where we can link the drugs to the polymer backbone, and these link can be then cleaved by water or enzyme. So here are some of the advantages and limitations of polymer drug conjugates. So the main advantages of polymer drug conjugates are they modify the chemical properties to increase the solubility, and they provide stability to more labile drugs. They increase the half-life of the drugs, reduce immunogenicity and toxicity, improve targeting, and drug conjugation via degradable bonds. So this is a controlled release, and it can be stimuli responsive delivery under specific conditions. For example, if we make the link enzyme specific, then based on the presence of enzymes in that particular area, the amount of drug will be released. And if we look at the limitations, biomolecule can lose activity during conjugation process, careful choice of chemistry and reaction sites. Yes, so if one of the reaction sites is blocking the drug drug receptor, or is blocking the reactivity of the drug, then it can actually lose its activity. Then purification of unreacted polymer biomolecules and any reaction products is necessary before in vivo application. Sterilization process now involves polymer stability as well. Most most of the polymers cannot be sterilized by the normal sterilization procedure, that is high temperature and pressure that we use for normal sterilization. And it can be viewed by regulatory authorities as a new drug entity, even though the drug molecule itself is well used. So it could take years and years along with high cost. These are some of the advantages and limitations of the polymer drug conjugates. Now, let's look at the next question. A gold surface, a gold surface was grafted with a polymer. The ends of this polymer are tagged with four pendant groups, namely A, B, C, and D. The pendant groups are weak acids. The modified isoelectric point of the entire polymer were calculated as follows. A has a isoelectric point of 4.5, B 5.5, C 7.4, D 9. These particles are loaded with a positively charged drug on the surface using electrostatic interaction in PBS, pH 7.4. Which of the following will have minimum loading? I'll give you some time to read the question and then we'll see if anyone wants to answer. The screen is visible, right? Can anyone unmute and let me know?
Yes, ma'am. Yes, ma'am.
Thank you. Is anyone ready to answer?
Yes, ma'am. I think A option. 4.5 pH.
Option A. Okay.
Yes, ma'am.
Option C.
C. Okay.
Option A, ma'am.
Okay.
Option A, ma'am.
Okay. Anyone else?
Is it the answer D?
Okay.
Uh, because it would be positively charged. pH below the pi.
Okay.
Expected to be positively charged, so loading is based on electrostatic interaction, so would expect minimum loading would be for D.
Okay. Very good.
Yeah.
Actually, that's the right answer.
Okay.
Very good. Okay. So, as you said, D is the correct answer, and you already explained the reason. So, pH, if the pH is less than the isoelectric point, it will be positively charged. And if the pH is greater than the isoelectric point, then it will be negatively charged. So, here our pH is 7.4, and these are the pi, and only 9 has a pH greater than the uh, is pH of the isoelectric point is greater than the pH 7.4. So it will be positively charged. And now, yes, when we load it with positively charged ions, it will repel it. But if we load it with negatively charged, it will be more loading. So since it is asking for positively charged and which will have the minimum loading, D option will be the correct answer. It will repel all the positively charged drug and it will have the minimum loading. Okay. Next question. Which one of the following polymers degrade hydrolytically by near zero order kinetics? Which one of the following polymers degrade hydrolytically by near zero order kinetics? The options are polylactides, polyesters, polyanhydrides, polyamino acids, polycarbonates, and polyamides.
Polyanhydrates.
Sorry?
Yes, ma'am. Polyanhydrides.
Okay.
Polyamides.
Okay. Anyone else has any other answer?
Polyamides.
Okay.
Polyamide.
Polyanhydrides.
Okay. Okay. Uh, I can see someone raising hand. If you raise your hand, I won't be able to see you. So it's better that you unmute and answer directly because I'm switching screens, so I'm not able to see if someone is raising hand or typing in the chat. Okay, so those of you who answered polyanhydrides, yes, you guys are all correct. It's polyanhydrides. So here how it is, it undergoes hydrolysis, and if you go through the lectures, it is directly mentioned there. Polyanhydrides produces near zero order release kinetics and the constant rate of release due to surface degradation only. And in the surface, these hydrolysis takes place. And this is here is a comparison between different comparison of the hydrolytic cleavage between different bonds, anhydrides versus esters and amides. So anhydrides have faster erosion compared to esters and then amides. Okay. Okay. We'll move on to the next question. Uh, Before we proceed, does anyone have any questions in the previous questions, in any of the previous questions before we move forward? I guess no. Okay. Okay, so the next question is, which of the following are correct with respect to PLGA particles? You have to choose two options. The options are, it is a non-biodegradable polymer, it can be used as a vehicle in gene therapy, they can degrade at gastric pH, they have not been used clinically, it is not a copolymer, they can be extracted from chitosan based products. Anyone would like to answer? Which of the following are correct with respect to PLGA particles?
It can be used as a vehicle in gene therapy and can degrade at gastric pH.
Okay.
Option second and third, ma'am.
Okay.
Option second and third, ma'am.
Okay. Does anyone have any other answer apart from these two options? Okay. So you guys are correct. The right answer is it can be used as a vehicle in gene therapy and it can degrade at gastric pH. So PLA, PGA, and PLGA, these polymers are most extensively used biodegradable polymers. They are FDA approved, are used in clinics, They're used extensively as particles in drug and gene delivery, are also used in tissue engineering scaffolds, and they can be hydrolyzable into lactic and glycolic acids at which are normal physiological products, and can be metabolized by body into carbon dioxide and water. And it is catalyzed by acids and bases. That's why it can degrade at gastric pH. Okay, we'll move on to the next question. What are the advantages of using polyethylene glycol in drug delivery application? What are the advantages of using polyethylene glycol in drug delivery application? You have to choose two options.
Has well-developed conjugation chemistry and non-toxic immunogenic can be produced under GMP. Good manufacturing.
Okay. Anybody else?
First and second option.
Okay.
It has well-developed conjugation chemistry, can deliver cargo intracellularly very effectively.
Okay. Anyone else?
First and second.
Okay. Anyone else would like to answer?
Option 2 and 5.
Okay. Okay. So here is the answer. Those of you said first two options, those are correct. It has well-developed conjugation chemistries. It is non-toxic, immunogenic, and can be produced under good manufacturing practices. So this is the information that is given in the lecture itself. If you guys go through the lectures, you'll find the same information. Polyethylene glycol or PEG. It is very hydrophilic, highly biocompatible polymer. The backbone of the polymer is highly flexible. That gives its properties of molecular windshield wiper, and it is soluble in both aqueous and organic solvents. So it has well developed conjugation chemistries. It is non-toxic, non-immunogenic, can be produced under good manufacturing practices, and of course it is FDA approved. Okay, we'll move on to the next question. If a particle takes time t to diffuse L millimeter, how long will it take to diffuse 4L millimeter?
40.
16 T, ma'am.
Okay. Anyone else would like to answer? If a particle takes time t to diffuse L mm, how long will it take to diffuse 4L mm?
Forty.
Okay.
40.
Okay.
40, ma'am.
Okay. Anyone else has any other option as their answer? Yes, anyone else would like to answer? If a particle takes time t to diffuse L mm, how long will it take to diffuse 4L mm? Anyone else has any answer other than 4t?
16T, ma'am.
Okay. Anyone else? Okay. Okay. The 16t is actually the correct answer. Here we'll use the equation xRMS equals to under root 2 tt, where x is the diffusion, d is the diffusion coefficient, x is the distance of diffusion, t is the time t, and d is the diffusion coefficient. And if you can solve it like this: x equals to under root 2 dt, so x square equals to 2 dt. The first one is L and time is t. The second one is 4L, so it will square, and then 2 dt. So the t will be 4 square, that is 16t. So the correct answer is 16t. Okay. I hope everyone got the answer.
Yes, ma'am.
Okay. Okay. We'll go to the next question. Consider that a drug is loaded into two separate reservoirs whose drug releasing areas are in the ratio 2 is to 1 and loading concentration of drugs are in the ratio 1 is to 2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible, that drug diffuses through a semi-permeable membrane in both the cases. I'll guys give you some time to read the question. Consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio 2 is to 1 and loading concentration of the drugs are in the ratio 1 is to 2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. If you guys went through the reservoir systems, you'll be easily able to solve this question. Did anyone go through the reservoir systems in the previous lectures? Hello? Am I audible? Hello?
Yes, you are.
Okay. Okay, so did anyone go through the lectures, the reservoir systems, this part? Or should I give you guys more time to solve the question and then we'll move on to the answer? Should we wait or move on for the answer?
I think you're good to move on to the answer, madam, from my side.
Yes, ma'am. Yes, ma'am.
Okay. If anyone is trying to solve, then please let me know. Okay, I guess we'll move on to the answer. So the answer is 1. So this is the equation that is used in the membrane reservoir systems, where m is the mass of the drug released, a is the area, d is the diffusion coefficient, uh, cs is the concentration, loading concentration, l is the length, and t is the time, and k, wait a minute guys, I think I'm missing something. Okay, you guys can figure this out from the lectures itself, it is more well explained there. But if you see the equation, the first, that is drug is loaded in two separate reservoirs whose drug releasing areas are in the ratio of 2 is to 1. So this 2 is to 1 is the area, that is A1 and A2 given here, and then loading concentration of the drugs are in the ratio 1 is to 2. CS, which is the loading concentration, is in 1 is to 2, and we need to determine the ratio of mass of drug released in the same amount of time. So the mass of drug released is m1 is to m2. So if you multiply this, you'll straight away get 1, which is the correct answer. Okay, we'll move on to the next question. Consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in a 1 milligram. Given the density of the material is 1.3 gram per ml, pick 2. I'll give you guys some time to read the question again and solve. For those who came late, this is the question that we are discussing. Consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in a 1 milligram, given the density of the material is 1.3 gram per ml.
Option second and third, ma'am.
Second and third. Okay. Anyone else?
Option 4.
Sorry?
Fourth option.
Fourth.
10 to the power 7. Yes.
Okay. Anyone else? Okay, anyone else has any answers? Consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in a 1 milligram given the density of the material is 1.3 gram per ml.
Madam, the volume will be 4 by 3 pi r cube.
Okay. Yes. If you're asking, yes.
No, I'm just, do you need to calculate the volume?
Yes.
4 by 3 pi r cube.
Yes.
And also the conversion of micron to centimeter.
Yes.
And then volume times density.
Yes.
And then 1 milligram should be converted to gram divided by, 0.01 divided by volume multiplied by the density.
Okay. So did you get
Is
it
that,
right?
is that yeah.
Can you say a number?
I think it was either 14.69 times 10 to the power of 9. And the other one, 0.1469 times 10 to the power of 10. 0.14, is it?
But is it the same option? 14.69 and 0.14?
No. Yeah, the 14.69 is the other option would be 1.4. To the power of 8. 0.14. No. Would it be 1.469 times 10 to the power of 8 and 14.69 times 10 to the power of 9?
What about others? Anyone else has any other option as their answer? I'll wait for one more minute, and then we'll move on to the answer. You already gave the hint, I guess. So please solve, guys, and let me know what your answers are. I'm sorry. This is Kristen William Mathumali. What you are asking, I didn't get. Is the week problem solving recording available? Do you mean this week or last week? Last week's was the link was shared with you people. This week's recording will also be shared. Okay. Like someone was saying, we have to convert to the volume and then use the density. So that is what we have to do. But you have to solve very carefully because a slight change in the decimal point will give you a wrong answer. So these are the correct answers: 1.469 into 10 power 9 particles per ml and 0.1469 into 10 power 10 particles per ml. So first, the diameter 1 micron, we can convert it into meter, which is 10 power minus 6 meter. Then volume of one particle will be 4 by 3 pi r cube. And the answer will come in meter cube, which is 0.5233 into 10 power minus 18. And the given mass is 1 milligram, density is 1.3 gram per ml. So the volume will be mass by density, which is 1 mg by 1.3 mg per ml into 10 power 3 mg per ml. I converted both to milligram, and then this will give you a value of 0.769 into 10 power minus 3 ml, and 1 ml has 10 power minus 6 meter cube, so we can say 0.769 into 10 power minus 9 meter cube in present in per ml. So the number of particles would be 0.769 into 10 power minus 9 meter cube per ml by 0.5233. The individual particle volume 0.5233 into 10 power minus 18 meter cube, which will give you 1.469 into 10 power 9 particles per ml, or it can be also written as 0.1469 into 10 power 10 particles per ml. I hope the answer was clear. Hello. Can anyone unmute and let me know if I'm audible or
Yeah, we got it. We got it.
Okay, good. Okay. So we'll move on to the next question. The next question is, reservoir system refers to. It refers to a system saturated with drug surrounded by degradable membrane, or a systems with zero order release rate, all systems with first order release rate, systems which have non-degradable membrane and are supersaturated with drug, all systems with second order release rate, systems with a semi-permeable membrane which degrades with time. I'll give you guys some time to read the question again and let me know what you think the answer is.
Madam, is this supersaturated and non-degradable?
Supersaturated, non-degradable. Okay, you're saying the fourth option. Systems which have non-degradable membrane and are supersaturated.
Is that the answer?
Okay, we'll wait.
Option 1.
Option 1, a system with drug surrounded by a degradable membrane. Okay. Anyone has any other option as their answer? Okay, anyone else has any other option as their answer? Reservoir system refers to a system saturated with drug surrounded by a degradable membrane. All systems with zero order release rate, all systems with first order release rate, systems which have non-degradable membrane and are supersaturated with drug, all systems with second order release rate, systems with a semi-permeable membrane which degrades with time. Okay, anyone has any other option as their answer? What is the reservoir system?
Option number 4.
Systems which have non-degradable membrane and are supersaturated with drug. Okay. Anyone else? Anyone else would like to answer? Okay. So you guys are correct. The correct answer is systems which have non-degradable membrane and are supersaturated with drug. So this is the definition that was given in the lecture itself. A reservoir system is a supersaturated drug reservoir surrounded by a non-degradable polymer membrane. It can have a planar configuration or reservoir above a polymer membrane. Could have cylindrical configuration. Most commonly used polymers, silicon elastomers, could achieve nearly constant or zero order release rates. Okay. So many of you joined just now when we have already discussed all the questions. I would like to request you guys to join around 6 p.m., which is when we start the session, so that you don't miss the entire discussion. But for rest of the people, I will go through the questions again we'll go through once again. Those who joined late, we'll discuss them. Okay. So we started with the topics that was covered this week: biomedical polymers, polymer drug conjugates, diffusion control system, controlled release reservoir system. I've already gone through all the questions, so I'll just quickly go through them. If the new people who joined later, they have any doubts, then they can stop me at any point they want and we can discuss it again. So the first question is, for a given polymer, rank the glass transition temperature Tg, melting point Tm, and crystallization point Tc from lowest to highest. So the option will be second option, Tg, Tc, and Tm. First the glass transition temperature, then comes the crystallization point, and then the melting temperature. This plot you can easily get in the if you go through the lectures. Glass transition temperature Tg is the temperature at which a polymer undergoes a transition from a hard glassy state to a rubbery state, and Tm, which is the melt transition temperature Tm, or crystallizing melting point, the temperature at which all crystalline regions melt, that is crystallinity, disappears, and Tc is the crystalline temperature. So the option will be Tg, Tc, and Tm. The second question was, which of the following statements is not a limitation of polymer drug conjugates? We have to select two statements. So, not a limitation, that means we have to select two advantages of polymer drug conjugates. If you go through the options, biomolecule drug can lose activity during conjugation process. This is basically a limitation. Purification of unreacted polymer, biomolecules, and any reaction product is necessary before in vivo application. This is also a limitation. Sterilization process now involves polymer stability, another limitation. Can be viewed by regulatory authorities as a new drug entity. This is also a limitation. Polymer drug conjugates can improve bioavailability of many poorly soluble drugs. This is an advantage. If non-compatible, they can trigger inflammatory reactions, another limitation. Then polymer drug conjugates can be made targeted for specific applications. This is another advantage. So the two statements would be polymer drug conjugates can improve bioavailability of many poorly soluble drugs, and polymer drug conjugates can be made targeted for specific applications. These were the options. We also went through the advantages and limitations that were taught in the lecture. And then the next question. A gold surface was grafted with a polymer. The ends of this polymer are tagged with four different pendant groups, namely group A, B, C, and D. The pendant group are weak acids. The modified isoelectric point of the entire polymer were calculated to be as follows. Group A has an isoelectric point of 4.5, B 5.5, C 7.4, D 9. These particles are loaded with a positively charged drug on the surface using electrostatic interaction in PBS, that is pH 7.4. Which of the following will have minimum loading? So the correct answer is D. D has an isoelectric point of 9, and this is greater than the pH, which is 7.4. So here, the at isoelectric point the charge is neutral, but at pH less than the pH of the isoelectric point it is basically positively charged, and at pH greater than the pH of the isoelectric point it is negatively charged. So in this question the isoelectric points are given here and the pH is 7.4. So if you see, D has an isoelectric point of 9, which is greater than the pH 7.4. So it will have a positive charge. So it will have a positive charge. Now the question is saying these particles are loaded with positively charged drug on the surface using electrostatic interaction. So if the particle is already positively charged and we are further loading it with positively charged drug, it will repel these positively charged particles. So the option D, that has an isoelectric point of 9, will actually repel these positively charged drugs and will have the minimum loading. So option D is the correct answer. Guys, let me know if you guys have any problem in when I'm explaining the answer. I'm going through it very fast because we already discussed these questions in details. Okay, which one of the following polymers degrade hydrolytically by near zero order kinetics? So the option will be polyanhydrides. Polyanhydrides produces near zero order release kinetics with a constant rate of release due to surface degradation, and the susceptibility of the hydrolytic cleavage of different bonds is as follows, which is anhydrides greater than esters and which is greater than amides. So anhydrides will have faster erosion compared to esters and amides. The next question is, which of the following are correct with respect to PLJ particles? It is a non-biodegradable polymer. No, it is a biodegradable polymer. It can be used as a vehicle in gene therapy. Yes. They can degrade at gastric pH. Yes. They have not been used clinically. No, they are used in clinics. It is not a copolymer. No, it is a copolymer of PLA and PGA. They can be extracted from chitosan products, base products. No. So the correct answer for this question would be, it can be used as a vehicle in gene therapy and they can degrade at gastric pH. So the next question is, what are the advantages of using polyethylene glycol in drug delivery application? What are the advantages of using polyethylene glycol or PEG in drug delivery application? We have to select two options. It has well-developed conjugation chemistries. Yes. It is non-toxic, immunogenic, and can be produced under good manufacturing practice. Yes. It is highly hydrophobic and biocompatible. No. Can be easily phagocytized by immune cells. No. Can deliver cargo intracellularly very efficiently. No. So the correct answers will be, has well-developed conjugation chemistries and non-toxic, immunogenic, and can be produced under good manufacturing practice. This is all the information that was given in the lecture. If you go through the lecture, you'll be easily able to figure out the options. The next question is, if a particle takes time t to diffuse Lmm, how long will it take to diffuse 4 Lmm? Here we'll use the equation x RMS equals to under root 2 dt. So if a particle takes time t to diffuse Lmm, this length of diffusion is here x RMS. D is the diffusion coefficient and t is the time. So if you put this L and t, then here is how you can solve it. X equals to under root 2 dt. So x square equals to 2 dt. Then for L, the time of diffusion is t. Then for 4L, the time of diffusion will be 16t. Now, the next question. Consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio of 2:1, and drug loading concentration of drugs are in the ratio of 1:2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. If you guys go through the reservoir systems in the lectures, you'll find this equation. Mt equals to AdKCST upon L. So here we are given M, which we have to find out. That is the mass of drug released in the given amount of time t. And we have also been given area, drug releasing areas A, and loading concentration of drugs, which is CS. So according to this equation, M is directly proportional to ACS. So we have to find M1 is to M2, which is equals to A1CS1 upon A2CS2. A1 by A2, that is the drug releasing areas, is here 2 is to 1. So this is 2 is to 1. Then drug loading concentration in the ratio of 1 is to 2. So this will be 1 into 2, 1 by 2. So if we multiply this, we'll get 1. So the drug releasing concentration, drug released in the same amount of time for these two reservoirs will be in the ratio of 1. And the next question was, consider a microsphere of diameter 1 micron. Calculate the number of such particles that would be present in 1 mg given the density of the material is 1.3 gram per ml. So you can solve it like this. The particle diameter is 1 micrometer, which is 1 10 per minus 6 meter. And the volume of one particle can be calculated by using volume of a sphere, which is 4 by 3 pi r cube. 4 by 3 pi r would be here 1 by 2 into 10 per minus 6 cube meter cube, and the value is 0.5233 into 10 per minus 18 meter cube. Then the mass given here is 1 mg, density 1.3 gram per ml. So we can calculate the volume from there, mass by density, which comes to 0.769 into 10 per minus 3 ml. If we convert these to meter cube, so the volume would be 0.769 into 10 power minus 9 meter cube per ml. And hence the number of particles, total number of particles would be this volume divided by volume of one particle, which is 0.769 into 10 power minus 9 upon 0.5233 into 10 power minus 18. So the answer we get is 1.469 into 10 power 9 or 0.1469 into 10 power 10 particles per ml. The next question was, reservoir system refers to all a system saturated with drug surrounded by a degradable membrane? No. So the correct answer is systems which have non-degradable membrane and are supersaturated with drug. If you read about reservoir systems in the lectures, you'll get this direct definition from there. A reservoir system, which is a supersaturated drug reservoir surrounded by non-degradable polymer membrane. Okay. Okay, now you guys let me know if you faced any problem in any of the question, or if you want me to discuss any question once again. We can go through it once again. Or anyone has any other questions?
Ma'am, I wanted to ask if there's anywhere else we can see the recordings of this sessions.
Yes, this session is recorded and the link will be shared with you people.
Right, ma'am.
Did you guys receive the last time's recording link? If yes, then this will be easily available to you.
I wanted to ask if I could get the last week's as well, as I couldn't receive it.
We had shared the link with the NPTEL people.
Right, ma'am.
I don't know if they shared with you people. I'll get back to you on that.
Yes, ma'am. Thank you, ma'am.
Yes, good evening, madam.
Yes.
As what sir discussed now, as the same problem was faced by me also, madam. Today only I opened that what are the question answer, what
Okay.
previous for lecture 1.
Okay.
Today I click on that link. I need to listen that discussion due to some problems. I was absent for that session.
Okay.
Actually, I need to know what is the question answer round, but even I also difficult to see that thing, madam.
The recording is shared on YouTube as well.
Okay.
Okay. I think you guys still haven't received the link. I'll try to share the link here in the chat if anyone needs here. We have also shared this with the NPTEL team, and they'll share this with you, I think.
And in that week 2 classes, in that biopolymers, biomedical polymers,
Yes.
in that session, A polymer, B polymer,
Can
you gave the
you tell me
examples.
the final answer you are getting?
You discussed about A and B, combination of A and B polymers, but what are the examples comes under that A and B?
I'm sorry, I'm not able to follow what you are trying to ask.
Actually, in week 2, almost 4 sessions are there, madam.
Okay.
In that first session, biomedical polymers.
First, okay.
In that biomedical polymers, they explained A monomers like that, and later he explained A polymer, B polymer, combination of the A and B polymer.
Okay. I think he
So,
was
what are the examples?
okay. Okay. So the block polymer or conjugation polymer you are saying?
Yes, madam.
Okay. Okay. Yes, like so that means you can combine two different polymers. So
Okay.
PLJ, which is polylactic co-glycolic acid, is
Mm.
basically a combination of two polymers, polylactic acid and polyglycolic acid. These two polymers, when they are combined, it gives PLG. That's a different polymer. So that is what you can combine two different polymers A and B to get a different polymer.
And one more question, in the implants, we are using the polymers. But
Yes.
in that class, the what they were discussing is means so the polymers which are used for the implant, they won't change any activities.
Yes.
After completion of that work of that plant implant, we need to remove that implant from the body, like that they are telling.
Yes.
So then, what purpose we are using that polymer?
To prevent any reaction. We don't want any immunogenicity. We don't want your immune cells coming to the polymer and show any reaction to it. So to prevent that reaction, we are using those polymers.
So by using that polymers, the drug is released in the body without affecting any toxic adverse effect, whatever it may be.
Yes. Yes.
Okay, ma'am. Thank you.
Okay. I have shared the YouTube link of previous session in the chat box if anyone wants to uh, get the link. And if anyone else has any other question or wants me to go through the question again, any question again of this session or previous session, we can discuss it again.
Ma'am, can you share your mail ID?
I'm sorry.
Can you share your mail ID?
Uh, and what would you need that for? For the questions or anything else?
And
Like,
other purpose like future careers or
so
PhD.
the forum is there, NPTEL forum. There you can post your questions. There are other teaching assistants responsible for solving these problems. You can post your questions there. They'll be able to solve your questions, queries.
Okay.
Okay. But if you have any questions that you want to ask from this session or any doubt regarding this session or previous session or the lectures, then you can mail me in this email ID. I've put my email ID in the chat box.
Thank you, ma'am.
No problem. Anyone else has any other question or any doubt? Where can I upload assignment work? If you join the portal, there you can you can submit the assignment work in the portal itself. Or if you are facing problem in uploading the assignment, you can post it in the forum. People are there to help you how to get access to the portal or how to upload the assignment.
Hello, madam.
Yes.
Madam, actually, under that last 10th question, submit answer, it is showing. When we click on that one, your week one assignment is submitted, it is showing like that.
So your assignment was submitted when you were trying to submit one answer, is what you're saying?
What I am telling means actually how we know whether the assignment is submitted or not. How we know?
Oh, I'm sorry, I have not seen that portal, but there is a forum where you can post this question, and other people, they know the technicalities, so they can help you better.
Okay, madam.
Hello, ma'am.
Yes, ma'am. Madam, actually, for assignment submission, you sending another separate link. When we click on it, that question paper will be opened.
Okay.
When it is opened, we are giving the answer. At last, we submit. We need to click on submit answer. Then it is showing yes, your week one assignment is submitted.
When you just open the assignment, then it is saying submitting, is it?
No, madam. After opening, what are the answers I gave?
Hmm.
At last, if I click on that submit answer, if I clicked on it, it is showing yes, thank you for successfully for week one assignment we submitted.
Okay. And then what
So
is?
it is not no issue, madam. It is submitted.
Yes, yes, it is submitted.
For that, madam. Actually, I thought for week one assignment, today or tomorrow is last date.
Okay. No, if it
That
says
let
it is
is
successfully submitted, then it is submitted. Until now,
okay,
only
madam.
week one assignment was due. Next week you'll get the week two assignment. So yes.
Okay, okay, madam.
Okay.
Thank you, madam.
No problem.
Hello, ma'am.
Yes.
Ma'am, actually, how we will able to know the score of our assignment that we have submitted?
Uh, that I'm not sure. You can try posting in the forum once, or I'll try to find out and let you know in the next session. We don't handle the forum or the assignment grading those things, so I'm not sure how you'll be able to do it. Yeah, but I can ask and let you know.
Okay, ma'am. Thank you.
Okay. Eighth question. One second. Okay. Okay. Someone wants me to answer eighth question again. We'll go through that. So here is the eighth question. Consider that a drug A is loaded into two separate reservoirs whose drug releasing areas are in the ratio 2:1 and loading concentration of drugs are in the ratio 1:2. What is the ratio of mass of drug released in the same amount of time for these two reservoirs? Assume that the reservoirs are flat and non-erodible. The drug diffuses through a semi-permeable membrane in both the cases. So if you guys go through the lectures, this is the equation that you'll come up with. Mt equals to ADK CST upon L. Here, the these values are given. So drug A is loaded into two separate reservoirs whose drug releasing areas. So A here is the drug releasing areas, and loading concentration of the drugs are in the ratio 1:2. CS here is the loading concentrations, and it is asking for ratio of mass of drug released in the same amount of time. So the mass of drug release is the M. So now if you see the equation, Mt equals to ADK CST upon L, the mass of drug release is directly proportional to the area of drug release and loading concentration. So we can directly solve it by using the ratio M1 S2 equals to A1 CS1 upon A2 CS2. A1 A2, the drug releasing areas ratio, which is 2:1, into CS1 CS2, which is loading concentration ratio 1:2. So M1 by M2 will be equals to 1. So the answer for this question is 1, and the mass of drug released, ratio of the mass of drug released in these two reservoir system is 1. I hope I answered your question. Alagamai G. Anyone else has any other question or doubt? We can go through it once again. We'll wait for some more time. If nobody has any other questions or doubts, then we'll close this session. I'll show you guys the questions again. So if you guys feel like you need some more explanation in any question, you can let me know. Can you explain third question? Okay, sure. So third question here is, a gold surface was grafted with polymer. The ends of the polymer are tagged with 4 pendant groups, namely A, B, C, and D. The pendant groups are weak acids. The modified isoelectric point of the entire polymer were calculated as follows. So these are the isoelectric points with respect to the group. A has the 0.5, 4.5, B 5.5, C 7.4, D 9. So these particles are loaded with positively charged drug on the surface using electrostatic interaction at pH 7.4 in PBS. So which of the following will have minimum loading? So here is the theory that we are going to use, that is, if pH is less than the pH of the isoelectric point, the particle would have a positively charged, and at pH equals to isoelectric point it will have negative electrically neutral or neutral charge. If pH is more than the pH of isoelectric point, it will have negatively charged. So here pH is 7.4, 4.5 and 5.5 have a pH less than 7.4, so they'll have uh, negatively charged. Then pH 7.4, it will have neutral charge, and D, pH isoelectric point 9, will have a positively charged. Now we are loading these particles with positively charged drug. So and we need to find out which has a minimum loading. So the one that will have a minimum loading will be the one most positively charged, because it will repel the positively charged drug. So 9 here, which has a isoelectric D here, which has a isoelectric point 9, will have a positively charged because it has pH more than 7.4. So it will have the minimum loading. So the correct answer is D. Okay. I'll scroll through the questions. You guys let me know if you want me to discuss any question once more. Okay, anyone else has any doubt or want me to explain any question again? Yes, hello Darshan. Do you have any doubt in any question? Yes, this PPT will be shared where the assignment is provided. The one that we are discussing now is the previous year assignment. Your new assignment will be in the portal. You can get it from there. Okay, anyone has any questions, any doubts in this, any doubts in the questions that we solved today, or any other questions? The link of this PPT is shared in Google Drive, and the link will be, the PPT is shared in Google Drive, and the link will be shared with you people. We have already shared with NPTEL team. I think they'll share this with you people. Yes, Aarti. Yes, anyone has any questions, any doubts, or want me to go through the questions we discussed today again? Anyone has any problems, any questions, any doubts in the questions I scroll through now, or in any question we discussed today, or in the previous assignments? You can ask me now. I'll wait for some more time. If nobody has any doubts or questions, then we will close this session. Yes.
Hello.
Yes.
Ma'am, can you share this link?
Yes, this link will be shared. This entire session was recorded and the YouTube link will be shared with you people. Also the PPT that I discussed today, that link will also be shared with you people.
Thank you.
In the chat box, the YouTube link I have already shared. You guys can access it from there, or the NPTEL team will also share the link with you again. Okay, anyone else has any questions? Can everyone unmute and say no at least? If nobody has any questions, then we'll close this session now.
No.
Thank you. Yes, others, please. At least let me know if you have any questions or unmute yourself and say no. Or you can type in the chat box as well. Thank you. Okay. I guess nobody has any more questions. We'll close this session here. This entire session was recorded. It will be uploaded on YouTube. And I'll also share the PPT in Google Drive. The link, the YouTube link and the PPT link will be shared with you people. I have also shared the link of previous session in the chat box if anyone wants to avail. Otherwise, the link will be shared with you from the NPTEL team. Thank you, everyone. See you in the next session. Bye.
Bye, ma'am.